Today we discuss about the thermodynamic potentials. So, thermodynamics, if you take thermodynamics, is nothing but it is a transformation of heat energy into mechanical work and vice versa. So, in order to state a thermodynamic system, so we will be representing the thermodynamic state of system in terms of certain selected variables like pressure, volume, temperature and entropy. So, there will be existing certain relation among these thermodynamic variables. So, if you take the first and second law of thermodynamics, it provides some relations which can be expressed as dq is equals to du plus pdv and dq is equals to tds we have. So, in this by combining these two equations, that is dq is equals to du plus pdv and dq is equals to tds, if you combine, we will get a tds is equals to du plus pdv we will get, and from this we can calculate the value of du, that is du is equals to tds minus pdv we are going to get. So, this is the basic equation which is connecting the first law and second law of thermodynamics. So, if you want to describe the complete system, we use certain energy terms or some functions of variables like pressure, volume, temperature and entropy, which are known as thermodynamic potentials. So, thus the thermodynamic potentials or thermodynamic functions are energy functions formed by combining the basic thermodynamic variables. So, the thermodynamic potentials are, there are 4 thermodynamic potentials. The first one is internal energy U, the second one you have Helmholtz function F, third one we call it as enthalpy or total heat function H we are going to call, and the fourth one we have this Gibbs function which we can represent with G. So, now we will discuss these 4. First we will discuss about internal energy U. This internal energy of the system is nothing but the energy which is possessed due to the molecular constitution and motion. So, this is what internal energy which is possessed. So, this is nothing but this is a sum of kinetic energy due to the motion of the molecules and potential energy due to the mutual attraction of molecules. According to first law of thermodynamics, there is certain function u of the variables which characterize the system. So, when a system passes from one state to another state, the change in internal energy does not depend on the path followed, but it depends upon the initial and final states of the system. For a complete cycle, if you take, the change in internal energy is 0, because the system returns to initial state after going final state, and again it will come back to the initial state. So, therefore, if you calculate here the change in energy, that is the change in internal energy, which can be given by du is equals to dq minus pdv. So, here du is equals to, we can write it as, in place of dq we can write tds minus pdv. So, this equation which we have, it describes the internal energy. Now, taking the partial differentiation of the internal energy with respect to the S and as well as V, we get like this, that is dou u by dou S with respect to V, we can get it as a T, and similarly dou u by dou V at constant S we can get it as a minus P. So, these are the relations connecting the internal energy U with thermodynamic variables S, V, T and P. So, since here du is a perfect differential here, by taking the partial differentiation, that is dou by dou V of dou u by dou S with respect to constant V, which is equals to dou by dou S of dou u by dou V at constant entropy. We can get this as dou T by dou V at constant entropy is equals to minus dou P by dou S at constant volume. So, this is the Maxwell's first thermodynamic relation we can get. Then after we have the second thermodynamic potential, that is a Helmholtz function F we have. So, from the second law of thermodynamics we have, that is du is equals to TdS minus PdV. So, now we consider the process in which the system exchange heat with surroundings and thereby maintaining the temperature constant. So, here the temperature is kept constant, then we can get here TdS, we can write it as a d of Ts we can write, because here T is constant. Now, the substituting the value of TdS in the above equation, we can get it as du is equals to d of Ts minus PdV. So, if you take this Ts this side, we can get it as d of u minus Ts is equals to minus PdV we can get. So, now this u minus Ts which we have, we can write it as a f here. So, if you write that, we can get it as df is equals to minus PdV. So, this PdV can also be written as work done, that is change in work done, dw we can write. Therefore, we have df is equals to minus dw. Here this u minus Ts is equals to f which we have written is known as Helmholtz free energy or work function we can call. That is the work done on the system is equals to the decrease in Helmholtz function. Next, for the above one, if you take infinitesimal reversible change, that is for a small change here, reversible change, an initial equilibrium state to final equilibrium state, the Helmholtz function changes as df is equals to du minus Tds minus sdt we can write. Therefore, in place of du we can substitute Tds minus Pdv, because we have calculated that the change in internal energy du is equals to Tds minus Pdv. If you write there, we can write it as df as Tds minus Pdv minus Tds minus sdt we can write. So, therefore, we can write the equation as df is equals to minus sdt minus Pdv we can write. So, here in the above equation, that is the temperature T and V are independent variables. Now, we will taking the partial differentiation of f, we can get as by taking the partial differentiation we can get as dou f by dou V at constant temperature is equals to, we can get it as a minus P, that is pressure, and partial differentiation of f if you take with respect to V, that is dou f by dou T with respect to V, if you take, we can get it as minus S, that is entropy. So, now here df it is a perfect differential, therefore, we can write the above equation as dou by dou V of dou f by dou T at constant volume is equals to dou by dou T of dou f by dou V at constant temperature. So, therefore, in place of dou f by dou T V, we have, that is S entropy, we can write dou S by dou V at constant temperature is equals to, we can write it as dou P by dou T at constant volume. So, this is what we have the Maxwell's second thermodynamic relation. Next, the third thermodynamic potential which we have is enthalpy or total heat function H we have. So, here the enthalpy is a thermodynamic property, and this can be written mathematically as H is equals to U plus P we can write. So, now differentiating this above equation, we can write as dH is equals to du plus Pdv plus Vdp we can write. Already we have written the change in internal energy du is equals to Tds minus Pdv we have. So, if you substitute there, we can get Tds minus Pdv plus Pdv plus Vdp we can get. So, from this finally, we can get the change in enthalpy dH is equals to Tds plus Vdp we can get. So, now taking the partial differentials of H, by treating entropy S and pressure P are independent variables. Therefore, we can write dou H by dou S at constant P is equals to T we can write, and dou H by dou P at constant S is equals to V you can write. So, now again as dH is a perfect differential, hence we can write it as dou by dou P of dou H by dou S at constant P is equals to dou by dou S of dou H by dou P at constant S. Therefore, already we have written dou H by dou S at constant P as T. We can write this equation as dou T by dou P at constant S, which is equals to dou V by dou S, because dou H by dou P at constant S is V we have. So, therefore, this equation dou T by dou P at constant S is equals to dou V by dou S at constant P. This is the Maxwell's thermodynamic relation, which is a third thermodynamic relation we have. Next, we have the fourth thermodynamic potential, which is known as Gibbs function G we have. So, from the definition of the enthalpy, we have H is equals to U plus PV. So, now if you write the change in enthalpy, dH is equals to du plus PdV plus VdP we can write. Therefore, by that is from the relation du, which we have as a TdS minus PdV. So, if you substitute in this equation, dH is equals to TdS minus PdV plus PdV plus VdP we have. So, therefore, this expression can be written as dH is equals to TdS plus VdP. After this, if the process, if you consider it as a isothermal, in which we can treat TdS as d of Ts we can treat, and as well as isobaric process, if you take the isobaric process, the change in pressure is equals to 0, that is we can write dP is equals to 0 we can write. So, therefore, we can write dH, that is the change in enthalpy, is equals to d of Ts, or we can write it as d of H is equals to Ts, which is equals to 0. Therefore, we can write it as H minus Ts is equals to constant. So, this H minus Ts is equals to constant is known as Gibbs function, and it can be denoted with G we can denote. So, that is we have G is equals to H minus Ts. For the small process, that is for an infinitesimal reversible process, if you take, we can write the change in its Gibbs function, that is dG is equals to dH minus TdS minus SdT we can write. So, from the change in enthalpy, that is we have dH is equals to TdS plus VdP we have. So, if you substitute this value in the above equation, we can get dG is equals to TdS plus VdP minus TdS minus SdT. So, therefore, we can write this dG is equals to VdP minus SdT we can write. So, this is the change in Gibbs we have. So, therefore, by taking the partial differentiation of G, here we will consider P and T, that is pressure and temperature, are independent variables. Now, by taking the partial differentiation, we can get dou G by dou P at constant temperature is equals to V we can get, and dou G by dou T at constant pressure is equals to, we can get it as a minus S, that is entropy. So, now again here dG is a perfect differential, hence we can write it as dou by dou T of dou G by dou P at constant temperature is equals to dou by dou S into dou G by dou T at constant pressure. So, by substituting the value of dou G by dou P at constant temperature as volume and dou G by dou T at constant pressure as a S, if you substitute, we can get it as dou V by dou T at constant pressure is equals to minus dou S by dou P at constant temperature. So, this is the Maxwell's fourth thermodynamic relation we have. These are the four thermodynamic potentials from which we have derived the Maxwell's relations, that is Maxwell's thermodynamic relations we have been derived. So, if you take the 4 thermodynamic potentials, that is first one if you take, that is the internal energy U we have. Internal energy is a function of entropy and temperature you have. Then the second one, Helmholtz function which we have, F, it is a function of temperature and volume we have. Then the third one, H, is a function of entropy and pressure we have. So, finally, the Gibbs function, G, is a function of temperature and pressure. So, which leads to 4 thermodynamic relations which are known as Maxwell's relations we are calling. These thermodynamic potentials, mainly they are useful to study the condition of equilibrium of system. Thermodynamic potentials has a great importance. If you see the importance of thermodynamic functions, so these thermodynamic functions are practical importance in studying the conditions of equilibrium of a system. If you take the internal energy is a extensive property. Its value is proportional to the quantity of matter constituting the system under consideration. The change in internal energy, that is du, when a system passes from one state to other state, it is independent of the path followed by between the two states. That is, if the thermodynamic system is from starting point to the final state, if you take, that is starting from one state, that is initial state to final state, it does not depend upon the path followed between these two states. It is independent of the path followed. So, therefore, the condition of equilibrium for a process in which the temperature and volume of the system remains constant, that is isothermal as well as the isochoric process. So, therefore, for this isothermal and isochoric process, we can be express dF is equals to 0, because we have dF is equals to minus PdV minus SdT. So, in this case isochoric process, the change in volume is 0, and for isothermal process the change in temperature is equals to 0. So, therefore, we can write dF is equals to 0. So, here in a isothermal isochoric process, only those states are stable in which the Helmholtz free energy is minimum. Then after we have Helmholtz free energy in any process at constant temperature is equals to the reversible work done by the system, that is minus dF is equals to dW. Therefore, minus dF is equals to dW we can write. So, we know that reversible work done is the maximum work which can be obtained from a given state, that is from a given change of state. So, that is in an isothermal process, the decrease in Helmholtz free energy is a measure of the maximum work obtainable from the change in state. Then if we go for enthalpy, enthalpy is an extensive property of the system. The change in enthalpy is equals to the quantity of heat given to the system for the change of state at constant pressure. Gibbs free energy G is also characteristic property of the system. It depends upon the thermodynamic state of the system. In an isothermal isobaric process, that is temperature and as well as pressure both are constant, the value of dG is equals to 0, which means that Gibbs function G is minimum we have. So, if you want to describe the complete system, we have used these thermodynamic potentials, functions or variables, pressure, volume, temperature and entropy, which we have called it as a thermodynamic potentials. So, we have discussed about these thermodynamic potentials. The first one, internal energy we have got, then we have got Helmholtz function, and then we have enthalpy or total heat function, then we have Gibbs function G we have. So, we have seen what is internal energy. Internal energy of a system is nothing but which is energy possessed due to the molecular constitution and motion. So, here due to the molecular motion we will get the kinetic energy, and due to the mutual attraction of the molecules we will get the potential energy. So, by combining these two, kinetic energy and potential energy, we will get this total internal energy we can get. So, then we have calculated this internal energy by using the first law of thermodynamics, and that is du is equals to dq minus pdv, in which we have been taken that among the 4 variables we have taken only S and V, that is entropy and volume as independent variables we have been taken, and the remaining 2 variables are dependent we have. So, therefore, in any system among these 4 variables only 2 are independent variables and the remaining 2 are dependent variables we have. So, from this we have calculated Maxwell's first thermodynamic relation we have calculated. We have got dou T by dou V at constant entropy is equals to minus dou P by dou S at constant volume we have got. Next, we have seen about the Helmholtz function we have seen, that also we have taken from the second law of thermodynamics, that is du is equals to T ds minus P dv we have taken. T ds is equals to d of Ts we have taken. So, by substituting this T ds in that equation we have got the Helmholtz function we have got as f is equals to u minus Ts we have got. So, after getting this Helmholtz function, we have considered that for a small change, that is a infinitesimal reversible change from initial equilibrium state to the final equilibrium state, we have calculated the Helmholtz function, that is change in Helmholtz function df we have calculated, and we have got it as minus s dt minus p dv. And in this we have taken 2 independent variables as temperature and volume we have taken as independent variables we have taken, and we have considered the partial differentiation of f we have been taken, and we have calculated the second Maxwell's thermodynamic relation as dou S by dou V at constant temperature is equals to dou P by dou T at constant volume we have calculated. So, with the help of this we have calculated the Maxwell's third thermodynamic relation, that we have got it as a dou T by dou P at constant S is equals to dou V by dou S at constant pressure we have got. Fourth Maxwell thermodynamic relation as dou V by dou T at constant pressure is equals to minus dou S by dou P at constant temperature we have calculated. So, these are the 4 thermodynamic Maxwell's relations which we have calculated.